Hello, my name is Hans Liljestrand, and I'm going to talk to you about our work, PACStack and Authenticated call stack. The problem we are addressing in this work is control flow attacks. These are attacks that exploit memory vulnerabilities in order to alter the control flow of the program. The traditional attack would maybe be the code injection attack, when an attacker exploits a stack buffer in order to overflow it and write shell code into the stack. So just writing code is of course not enough. You also need to make that code to be executed. And this is achieved by also corrupting the return address so that when the function returns, it will actually return into the shell code and start executing it. So the code injection specifically is not really viable anymore because modern defenses prevent that quite well. However, this control flow part here, that's still quite a useful technique, and it's used by code reuse attacks, when instead of injecting the code, you actually reuse parts of the already existing code in order to execute that in an attacker-controlled order. And it is specifically this return address protection part that we want to address and fix. So to achieve this, we are using ARM pointer authentication. So this is a new hardware primitive in the ARM CPU that allows approximation of pointer integrity. So this is all achieved by adding new instructions that allow the creation of message authentication codes that are embedded into the pointers, so that when the pointer is loaded back from memory, we can then verify that the message authentication codes still match the address in that pointer. This was introduced in the ARM 8.3a specification. It's currently used by recent Apple devices. Support on the software side is also already available in Linux and by the GCC and Clang compilers. So the pack itself, that's stored in the pointer itself. And now you might ask that how this is done. So this is possible because the address of a pointer is typically less than the 64 bits that the pointer occupies. So on a typical Ubuntu ARM installation, that might leave 16 bits for storing the pointer authentication code. How this is calculated is by using a tweakable keyed MAC, which takes as inputs the address of the pointer naturally, but then also a 64-bit modifier that's given by the instrumentation. And finally, a 128-bit key that is stored in a configuration register. So on Linux, for instance, the kernel would set these keys for each process, and then the process would just use them without being able to modify the keys themselves. So we know that message authentication codes are vulnerable to replay attacks, and it turns out that the same attacks also work on pointer authentication. So an example here, we will look at the instrumentation used by GCC and Clang to protect the return addresses. So what happens when function 1 is called, that we have this, the first thing that happens is this PAC-IA instruction, which is used to assign the return address, which in this case would be stored in the link register, LR. And then in the instrumentation, the stack pointer value is going to be used as a modifier. So this would be the value of SP. Unfortunately, the stack is growing and shrinking at runtime, so the value might actually repeat. Knowing this, the attacker might read out and store the current signed return address here in function 1, and then allow execution to continue. And here in function 2, we will see that again similar instrumentation code that again signs the current return address here using the stack pointer value. But the problem here is now that the stack pointer value is going to be the same as previously. Knowing this, the attacker can just inject the old value onto the stack and cause the program to incorrectly return to the other call site. And this is the problem we want to prevent in the context of pointer authentication. Our main idea is that we use instead of relying on just one static modifier or something, so a local modifier, we use a chain back of cryptographically bound return addresses. So in a sense, all the return addresses that we have at any time in the stack are all cryptographically bound to each other. So in practice, the chain would look something like this. So on the left here, you see what would happen in the first kind of function call where we just bootstrap, in a sense, the chain with one value, 0 in this case. And then all subsequent return addresses and authentication tokens are then generated by using the previous one as a modifier. And what's more, we reserve one register so that we can use that to securely store always the topmost authentication token. And this authentication token now is then specific to this whole call chain that we have currently active in the program. And when we need to unwind the stack, we can always use this topmost value to securely verify and retrieve the previous one from memory. And then, of course, update it into the same register again. And this quite nicely prevents reuse attacks and allows us to do very precise verification of returns. So using a chain MAC and securely storing the topmost token quite nicely prevents these typical reuse attacks that we looked at earlier. So considering this call graph here in the picture, we could consider a specific flow through it that goes from AC to the loader. At this point, the whole chain now incorporates the specific path through the program, preventing reuse attacks of specific return points in the chain. What's more, the topmost value is going to be in this register, so the attacker can't do anything to try to corrupt that. Unfortunately, there might be collisions in a chain that allows an attacker to corrupt previous values on the stack that, of course, are corruptible because they are in memory. So in this example, we could consider another control flow path through B, C, and again to the loader, such that although the chains are different, the topmost value might actually end up, due to a collision, having the same authentication token. And this then would allow the attacker now to replace the correct chain from C to A with the chain from C to B. In isolation, this is a relatively maybe weak attack because you have to replace the whole chain, but nothing would prevent an attacker from just repeating this attack and finding multiple collisions so that the attacker can do many of these false kind of forks in the chain when going backward. So what's worse is that PAC collisions actually turn out to happen surprisingly often. So for a 16-bit PAC, only after 321 addresses observed, it is already likely that collisions will be found. And this is also a problem inherent to the size of the PAC, so there's not much we can directly do about this problem. But what we realized is that we can prevent the attacker from recognizing these collisions. In essence, this means that an attack that otherwise could always be deterministically successful by just finding the collision, the attacker is again reduced to guessing attacks. And what's nice is also that we realized that we can use the same pointer authentication hardware to generate masks for hiding these collisions. So one interesting aspect of pointer authentication-based schemes is that they can be analyzed as crypto protocols. So in the paper, we actually prove security reduction for PACStack to the collision resistance of the PAC primitive itself. And this is also had some practical implications for our kind of implementation work, because essentially by undertaking these efforts of constructing this proof, we realized that we had this collision problem in the first place. So without trying to do these proofs, we would never have even realized that we need to do the masking that we then implemented and showed to be secure. We benchmark the PACStack using the C language benchmarks from SPEC CPU 2017. We compared it both with and without masking to the software-only shadow call stacks from LLVM, also to the pointer authentication, return address protection, what we looked at earlier, and finally to the stack canaries. The overheads in general were quite small and comparable to the other schemes, with masking incurring 3% overhead and without masking about 1% of overhead. So with PACStack, we have shown that we can use pointer authentication to achieve security quite comparable to shadow stacks. I think this is a nice example of how we can use these relatively general purpose mechanisms to achieve kind of new non-obvious security properties. But I also hope that this will not be the only example of this. In particular, now with both ARM and others coming up with quite a lot of these new and exciting runtime security mechanisms in their hardware. All of our source code is open source and publicly available. You see the Git link here. And I'm also happy to answer any questions you might have in a potential Q&A session here or via email or Twitter later. Well, thank you for your attention.